I'm Michael Walsh. I'm CEO of Midgard Consulting. I'm here with my colleagues, and my colleague Michael Potchek, Chris Oakley, Matt Good. And I wanted to take this opportunity to have a bit of a roundtable discussion about what I'll describe as the utility of the future. So let me start with you, Michael. When you think about where we are today with the utility industry, where do you think we are 10 years, 20 years from now? And what's the key challenge that the utilities are going to face?
For me, and it's a little bit based on my experience of where I came from, it's an understanding of the challenges utilities have to integrate renewables into their system and to be able to deliver power to their customers when the customers want it. We've seen this society really wants more and more renewables. Society wants to integrate renewables into the energy mix, but that intermittency, that supply of power being when the wind blows or the sun shines doesn't match the load. And utilities can absorb those renewables up to a natural breaking point until they can no longer balance the grid with their other resources. And then we're going to see things such as oversupply of wind, spilling wind, oversupply of solar. So we're going to have to spend that much more to oversupply renewables so that the utilities have enough power even on a cloudy day or a still day to deliver their customers. I don't know how they're going to achieve that and still kind of be efficient with costs.
So let me follow up on that question, and I'll ask you too, Chris. Technology solves all these other problems we have. Why can't technology just solve this problem of intermittency that Michael's talking about?
It's a little bit the nature of the medium or the actual entity we're working with electricity, which is hyper real time. It's the old analogy we've talked about, which is natural gas. You can line pack and that sort of thing. You can store that stuff actually in the transmission system and utilize it when you need it. Whereas with electricity, it's got to be right now, millisecond delivery, sub-millisecond delivery, or the whole thing falls apart and you have a blackout. Unless you can either isolate parts of the system and stick storage on them, or have dispatchables that, when the renewable drops off, the dispatchable picks up. But it kind of doesn't let you achieve that, that green revolution that people seem to be looking for now. So you need that real-time supply because people want power when they want it, and they're not going to be happy with intermittent power.
And Chris, I think you had a word that kind of resonated with me, is storage. And we see now, I see a lot of people looking to batteries as a solution to this problem. We're going to provide storage. We're going to buy batteries. Unfortunately, the vast majority of the ratepayers in North America, when they open their monthly electricity bill and they have a look at it, they're paying for energy. And so there's no way to really incorporate the cost of that battery into an energy charge. So there's going to have to be almost a training, if you will, of the electricity customer to be able to understand that they have to pay for this storage on top of the electricity when they simply turn off their light.
Not to mention, we need better batteries. So batteries are a limitation. They're a technology line in the sand right now that we are not going to easily get past.
So there's a lot to unpack here, but let me bring Matt into the conversation. The question, as I'm listening to Michael and Chris, the question that I want to pose to you is, what is this limit? Like, what's this percentage that's the magic line before problems erupt? And is it as simple as a black and white line, or is it just a higher tolerance for failures?
It's an interesting question. The line does depend. It does vary on the system you're speaking of. You're talking about whether it's a dense urban system, whether it's a system with a strong interconnection that can lean on neighbors when when the intermittents do drop off.
So let me just, can you just explain something? When we talk about neighbors, I know we talk about the grid. Just give us a little bit of the definition of the grid. Are we talking about a system grid, or are we talking about micro portions of the grid?
Sure. Well, at its simplest form, or the way that I can conceive of it, is that the grid is traditionally, it's the wires portion of the system that's traditionally been used to move the power from the generators, from the sources, to the users, to the load, to the...
So that includes both transmission as well as distribution?
Yeah.
Okay.
Yeah, I mean, different...
Well, so why is that hard? I think, Chris just talked about the microsecond, the timing issues, which is clearly different for electricity, which moves at the speed of light than, a physical gas like natural gas. But why can't you just parse out the grid into many little pieces? Why do we talk about the grid as this big machine that covers, all of North America?
Because at any one time, the supply and the use need to match in order for the frequency to be maintained. And if the frequency goes above or below 60 hertz, which is what...
But if I think of this as a puzzle, why can't each little piece of the puzzle have its own frequency?
It did before the grid existed.
Hey, Michael, let me. I got an idea. It's like you're sort of more financially founded, right?
Yes.
So think of it in terms of diversification. To diversify your risk. The smaller your grid, you're going to have fewer generators and fewer users, and one person switching on a light or plugging in a kettle is going to have a larger impact that has to be met with the load or the generation.
Yeah.
The broader your grid, the more users, the more generators, you've diversified that, where individuals' actions are less likely to impact the working of the grid as a whole. So a microgrid is simply the grid defined as smaller and smaller and smaller and smaller.
A university campus versus a province versus...
Okay. And then the challenge now is using computational power, using computers, using electronics to kind of keep that balance versus what was historically, going back to the early 1900s, was spinning pieces of steel to try and balance.
Okay, so my understanding is the grid grew up through a system where there was economies of scale to make larger and larger generators. And therefore there was efficiencies and economic efficiencies to build the grid larger and larger. I mean, correct me if I'm wrong.
Well, true, but there was an unintended consequence, which is the larger it got, the more robust it got. And let's put aside for the moment the fact that the larger it gets and the more complex it gets, there are potentially failures that start to creep in because your numbers are getting big, and a failure might cascade into some other areas. But as the grids grew large, and as Michael says, the sources got more diverse, and the uses got more diverse, there's a natural balancing out. So in our large North American grid, especially if I look at the eastern grid, which is synchronous, and then there's the western grid, which is also synchronous but separately from the eastern grid. But in the eastern grid, if you lose a 2,000 megawatt nuclear plant, it just drops offline. Nobody knows it happened except for the people at the plant. The system frequency does not budge, and frequency might be a bit of an issue for people that kind of think in batteries, because that's all DC current. We're talking about a synchronous AC system. All the machines are operating, they're turning together with each other. They're all spinning in the same frequency at the same time. Everything is kind of locked together, although maybe by rubber bands. So that's where we get some instabilities. And as Matt says, if there's a problem between supply and load, an imbalance there, you're going to actually drop the frequency or raise it beyond points that are going to be acceptable for some of the components. So there are kind of layers of complexity and technical issues that have to be dealt with. But again, going back to Michael's point, the smaller you make the grid, the interconnected grid, or its ability to drop out, the less diverse that system is, the more a single small event can actually take that piece of the grid out now, that microgrid.
Okay, so I'm hearing what you're saying. So we had the grid developed, and a really important part of the grid is that it's robust, that it stays together, and that even big events like an outage at a large nuclear plant doesn't necessarily cause cascading blackouts. But we began, and Michael, you were describing how we in society wants all this renewable generation. I mean, obviously there are benefits to having solar and wind and a diversification, to go back to the financial comparison you were making. Diversification makes sense. So my question to you is, the grid is the future and the utility of the future. Why can't we integrate some of the good stuff of the renewables and yet maintain the robustness of the the old school grid? And isn't that what microgrids do? Isn't it the ability to intermingle the micro with the macro that is really going to be the utility of tomorrow?
I believe that is the goal and the dream. One aspect of the traditional grid and the economies of scale around generation is that the large generators were sourced close to where the fuel sources were. A large hydroelectric dam at the mouth of the valley, a coal plant, a major coal plant at the mouth of the mine, and then there was the grid to bring it to the centers of usage. Now we're seeing with wind, and even more so with solar, that the location of sources isn't so much dependent. It can be anywhere the sun shines and there's sufficient real estate. And so that's where so instead of having to move the power so far from the place of the source to the area of usage, it's becoming closer. But so far, it's been an economic disparity in that the large generators are paid off, the mortgage is done. Those sources have been quite a bit more economic than the new ones that are coming on, and so we will get there, but it's interesting because this isn't a sense of starting from scratch to build a grid, to build a system with our current optimal resource mix, but how to transition from a centralized source and concentrated usage to the distributed system from where we are today to where we're moving to. So it's a complicating factor.
It's a tough renovation.
Yeah, it's a tough renovation, and
We're also moving from fuel sources, though, that used to be always available, so temporarily wideband. Now we're going to where there's definite windows of availability of energy, but the load wants to follow the load's pattern. It doesn't care about when the sun shines and when the wind blows. People still want to be able to, watch their TV or cook their food or run their refrigerator. So the problem is getting to be right now is the smaller you make these microgrids and maybe you get to a less diverse fuel source, how are you going to align the needs of the users within that microgrid with the fuel sources that it has available? And so either you put a big storage in there to get through the tough times when there's no energy, or you lean on your neighbors at that time. But if all of the microgrids are also not diverse, they're all running off the same fuel source, then you have a problem that everybody is actually aligned at the wrong time. So we don't have that market diversity that was originally gained by the grid when it expanded. We have to solve that problem.
So, is there a home for a big generator in the utility of the future?
I think there will be for a long time until storage gets 2 or 3 orders of magnitude better.
and by better, do you mean economic or the ramp?
Always economic. Always economic. But we need faster storage. The batteries have to get better. They have to be able to be charged faster, discharge faster, have much bigger capacity. Or we have to get used to dealing with the old methods of using pump storage. So you make a bigger lake and you pump more water.
What about a larger fleet of electric vehicles?
Well, we'd have to coordinate them. So there's going to be a really interesting market discussion to happen between the owners of electric vehicles so that they can actually be used as a coordinated fleet.
Okay, last question. 10 years from now, how much does the electric system, the utility system, look different than it looks today?
Have deeper penetration of renewables, and we have either solved the problem of storage, or we have to, as consumers of power, get used to less reliable grids.
Chris?
I don't know that consumers are easily going to want to get used to unreliable grids. The places that have that right now, like in some of the sub-Saharan African countries, are trying to get towards a reliable grid. So I'm not sure that consumers will be up for that. So I think we're going to have to deal with storage. We have to get storage figured out. We're probably a couple of inventions away from a better battery. Maybe that'll be the solution. There's going to be costs. None of this stuff is coming free, and it's all add-ons to the grid.
Matt?
When I think of the amount of time it takes to develop and permit a project, I don't think that there's a lot of space for the large-scale grid to develop much more, and there's just a shorter cycle time on PV installations, and even large pump storage projects. It's probably more than a decade to get one going. So I think we'll see more of the same. PV and the incremental iterations of battery technology.
And I think I touched on it. Do we start spilling renewables?
Yes, I agree to a great extent with what you said. I think 10 years from now, we're a far closer point to, if you will, the unsustainability of the current model. And I think that we have real problems that we're going to have to deal with. But I really think that by 2050, we'll have an unrecognizably different system than we are today. You either get wiser with every investment or richer, and I think we'll get a lot wiser over the next 10 years.